In our last video, we did a definite integral that required the trigonometric substitution technique. Here we're going to do the same integral, however, we're going to do the indefinite integral, which is a little bit more challenging. So in our last example, if you go back to that last video, you can see that we found that this integral turns into the integral of secant squared of theta after you make the substitution that x is equal to sine of theta. It turns out that we didn't need to have exactly the number 1 right here. Any positive number could have appeared here. And so I'd like to make the example just a little bit more general by replacing this 1 with some a squared. You could solve the problem in pretty much the same way. Instead of using x equals sine of theta, you would let x equal a times sine of theta. But everything else would proceed in the same way, and you would end up with 1 over a squared times secant times the integral of secant squared of theta, instead of just the integral of secant squared of theta. So now I'm going to go ahead and integrate this secant squared of theta. That is one of the basic integrals. It gives tangent of theta. And now here comes something that's a little bit more challenging than a typical just method of substitution scenario. Here we need to figure out what tangent of theta is simplified to if we use the variable x instead of theta. Our original integral was in terms of x, so our final answer should be in terms of x. To do this, we're going to end up making a right triangle that is agreeing with the formula that x equals a times sine theta. To make it more apparent how we're going to actually make that right triangle, let's rearrange this equation and solve for sine of theta. So all I need to do is divide both sides by a, and then I get sine theta is equal to x over a. Of course, the definition of sine is opposite over hypotenuse, so I'm going to make a right triangle where the opposite is x and the hypotenuse is a. That looks like this. I have my angle theta, the opposite side is x, the hypotenuse is a, and since this is a right triangle, I could use the Pythagorean theorem to figure out the length of the remaining side. Turns out that it's going to be the square root of a squared minus x squared. Now we can figure out what tangent of theta is using this right triangle. Tangent of theta, by definition, is the opposite side divided by the adjacent side. So the opposite side is x, divided by the adjacent side, and you get the expression x over the square root of a squared minus x squared. Now we're going to go back, replace this tangent of theta with this new expression. And the last thing we want to do is just simplify. We can multiply the 1 over a squared into this new expression that we have. And then we actually will get our final answer. The final answer is x over a squared times the square root of a squared minus x squared plus the constant of integration. So when you have to do indefinite integrals that require this trigonometric substitution approach, you often have to go through a type of reasoning like this where you make a right triangle to figure out what tangent of theta is or some other trigonometric function evaluated at theta.